Alright, so welcome back. We had a small challenge there. Power went off and therefore Wi-Fi went off as well. So welcome back. Now, before we had that disruption, I was saying that half-life, that is half-life. I was saying that half-life can be measured in two ways. We can measure half-life in terms of masses. Alright, we can measure half-life in two ways. The first one is in terms of masses. How long does it take for element X, whose mass initially we had 20 grams of X, for this 20 grams to decay so that we only have 10 grams, and we said that is the half-life of element X. And I've given an example. We say that if it takes 10 seconds for the initial mass to become half of whatever it was initially, that is half-life. Now, somebody could measure half-life in terms of activity, in terms of, is somebody trying to come in? Sorry? All right, okay. It's okay, we'll see about that. So the time taken for this one to decay so that we only have 10 remaining, then is called the half-life. Now, and I was saying that there is also a different way in which half-life could be expressed. We have said that radioactivity is measured using an instrument that we call a GM counter. A GM counter. And a GM counter records the activity per unit time. And I was giving an example, and I was saying that if you could pick a radioisotope like uranium-235, which is radioactive, and you have, say, like 100 kilograms of uranium-235. If you placed 100 kilograms of uranium-235 in front of a GM counter, then the GM counter would record a very high degree of activity, because we have so many atoms, so many nuclides that are disintegrating, decaying at the same time. If, on the other hand, you had the same uranium-235, but in this case you only have 0.04 grams, of course the number of atoms decaying per unit time is very small. And therefore, that would tell you, rather, if you placed uranium-235 in front of a GM counter, and the integrations per minute, or the count rate, that is, we call it counts per minute, for example. This is count per minute, meaning disintegrations or decays, the atoms decaying per minute. If, for example, the CPM, the disintegrations per minute was 200 CPM, that would tell you that we have so many atoms, so many nuclides of uranium. If after a given time X, the CPM becomes 100, it would tell you that the number of atoms, the number of nuclides of uranium has reduced to half of whatever we had initially. So this GM counter is also, or rather the counts per minute, or somebody could use counts per second, if at all the half-life is very small. So if at all you have a GM counter, you can also measure half-life by using this concept. And when you're using the GM counter, or the counts per minute, the half-life is defined as the time taken for the activity of this radioisotope to reduce to half of the initial activity. Of course, the units are CPM, counts per minute, or it could be CPS, counts per second. So the time taken for the activity to reduce from 200 to 100 is a half-life. And this could be, for example, 20 days, if that is the half-life. If the half-life is 20 days for uranium, then it would take another 20 days for the count rate to reduce to 50. This would be 20 days. And it would take another 20 days for the count rate again to reduce from 50 to 25 CPM, it would take another 20 days. etc, etc. So activity can be measured in terms of CPM or CPS, etc, etc. And again, just like we have done with the other concept, with the other method that we're using to measure half-life, there could be so many questions around the half-life of a substance by using this method. Let me just solve one. I hope we are not yet out of time. Let me see whether I can get yes, we can use this one. Consider a radioisotope X whose activity was measured and then plotted on a graph as shown below. This is activity. And let me have 0 here. 10, 20, 30, 40. All right. Now consider this radioisotope X, whose activity was measured using a GM counter and then plotted on a graph like the one I have here, and these were the results. Now the question is, what is the half-life of X from the data that you can get from this graph? And what you will do, you first of all need to understand that half-life is the time taken for the activity of our isotope here to reduce to half of whatever it was initially. For example, I could pick a time when the activity was 40 counts per minute, and that time was 0. Was it 0? No, it wasn't 0. It was here. So that time looks like it was 25. At minute 25, the count rate was 40 CPM. So after how long does the count rate become half of 40, which is 20? So I'll move along the graph like that and then get that figure. And from my work here, that looks like 80. And therefore the difference is 80 minus 25, that becomes 55. 55, 25, that's 0, that's 80, yeah. So the half-life for my radioisotope X is 55, because that is the time it took for the activity to decrease from 40 to 20. And I could pick 20 and 10. I could pick 20, that was minute 80, and I could also pick 10, and that was minute another one here. If at all my graph is plotted correctly, then the time taken from here to here should be the same as the time taken from here to here. If I took minute 30, the time at which the activity was 30 and the time at which the activity was 15, the answer should be the same, because half-life for a given element remains the same. For a given radioisotope, remains the same. So just like we were using the masses, you can also use the activity in counts per minute or counts per second to calculate the half-life for a given substance. I think that is it for today, unless there's a question. Any question on Facebook?
I can see. Ne?
All right. Any question on Zoom?
Unmute.
All right. I'm not sure whether we can. Are these able to hear me? These people.
They can hear you, but
they can't respond. All right. Any question? Those on Zoom? Any question? All right. I think we're fine. Then let's stop there today. We're going to pick it up from there. The next lesson we have. The next time we have a chemistry lesson. In the meantime, try as many questions as possible. Attempt to use the knowledge that you have gained here, so that when we meet again, you'll be better. Have a good day.